You think you understand how planets move. You've seen the illustrations in textbooks. A neatly spinning protoplanetary disk. Planets forming and continuing to orbit in the same direction like everything in the solar system follows a perfect choreography that nature has prearranged. Neat, plain, easy to understand, but here's the problem. That picture is wrong, blatantly, thoroughly wrong, to the point where you have to wonder if what you thought you understood about the solar system is really understanding at all. Because if all planets obediently spun in the same direction, then Venus is the boldest rule breaker you've ever encountered in astronomy. Let me make it clearer. Between 1991 and 1994, the Magellan spacecraft measured that Venus takes 243.25 Earth days to rotate once on its axis. It only takes 224.7 days to orbit the Sun. That means a day on Venus is longer than a year. And if that's not enough to make you uncomfortable, here's the real punch. Venus spins retrograde, while Earth, Mars, Jupiter, Saturn, Neptune all rotate prograde like a well-drilled team. Venus decides to spin retrograde, as if it's standing in the middle of the cosmic playground and shouting, "I want to go the opposite way from all of you." Got a problem with that? And if you're trying to hold on to basic physics knowledge that the solar system formed from a cloud spinning in the same direction, that angular momentum must be conserved, then Venus is shattering that intuition right in front of you. It's not just a little different. It challenges the entire story we tell about the birth of planets. And this is why I'm telling you this story. Because to this day, no one from 17th century astronomers to modern labs can fully explain why Venus spins retrograde. And if you feel a bit uncomfortable, good, because that feeling is the gateway to real understanding. Now, before we go further in this case, I need you to grasp a foundational physics principle. Actually, you've seen it when you sit on a swivel chair and pull your arms in, you spin faster. When you extend them out, you slow down. A figure skater does that on ice every day. That's conservation of angular momentum 1 of the universe's unbreakable rules. About 4.6 billion years ago, our solar system formed from a gigantic molecular cloud spanning tens of thousands of astronomical units, containing dust, hydrogen gas, helium, and a bit of heavier spice left by supernova explosions. That cloud had a very small rotation, very small, but there. And as that massive gas blob contracted, it started spinning faster, just like your swivel chair when you pull your arms in. The result is the entire system, the sun, planets, moons, all inherited the same original spin direction. Viewed from the sun's north pole, everything rotates counterclockwise. That's prograde rotation, the standard direction of the solar system. Mercury spins prograde, Earth prograde, Mars prograde. Jupiter spinning so fast it almost flings material out prograde too. In short, the whole family spins in the rhythm that nature initiated from the beginning. And according to theory, according to every planetary dynamics model, according to all the knowledge we've built over the past century, Venus should follow that general law. But as I said, Venus doesn't care. It looks straight at the law and goes the other way. No, it says, I'll spin retrograde, thanks. And this is where things start veering into a direction that any physicist finds both fascinating and uncomfortable. Because according to everything we know about planetary dynamics, Venus should be Earth's twin sister, an almost perfect copy. Look at the numbers. Venus's mass is 0.815 times Earth's. Its radius is only about 5% smaller, average density nearly equivalent, and both are in the terrestrial planets group, formed from the inner solar system. If you put Earth and Venus on a scale in the dark, you would have trouble telling which is which. And since these two planets were born from the same spinning disk with the same angular momentum origin, the most reasonable expectation is that they should rotate similarly. That's what astronomers believe for centuries, a completely reasonable belief based on the knowledge of the time. In the 17th century, Jean-Dominique Cassini observed dimly through Venus's thick clouds and reported that the planet had a rotation period of about 24 hours like Earth. Into the 18th, 19th centuries, people like Johann Hieronymus Schroeter and Giovanni Virginio Schiaparelli offered more refined numbers, around 20 to 30 days, all within a comfortable physics range, fitting intuition and causing no conflicts with the overall planetary picture. No one objected, and honestly, no one had reason to doubt. Everything made sense to a dangerous degree. Then in 1962, JPL decided to do what ancient telescopes couldn't: use radar to penetrate the clouds and directly measure Venus's surface motion. Goldstein's team fired strong radar signals from Earth, waited for the reflections to return, and analyzed the Doppler shift to know how Venus rotates. And that was the moment the slap to physics intuition was delivered without mercy. Venus doesn't rotate in 24 hours, not 30 days, not 100 days. It rotates in 243 days, and not painful enough, it spins retrograde. Imagine handing in your homework predicting 30 days, and the teacher returns it with 243 days retrograde. That's not an error. That's a declaration. You don't understand the problem. But science doesn't stand on a single measurement. So when the Magellan spacecraft arrived at Venus from 1990 to 1994, using radar mapping with accuracy down to parts per million, the entire 1962 result was confirmed absolutely. 243.25 days. Retrograde rotation, indisputable. And this is where the universe, with its characteristic mischievous tone, winks at us. You think all planets will obediently follow your laws? Cute. In physics, when you predict 30 days, but reality is 243 days retrograde, that's not a small mistake. That's the collapse of assumptions. That's a clear signal that something profound is hidden deep under Venus's 20 kilometers thick clouds. And it's that painful gap between reasonable expectation and completely opposite reality that opens one of the solar system's most intriguing mysteries. Why does Venus dare to spin retrograde? So to understand why that discovery was so shocking, we need to clarify a concept that seems simple but leads to a lot of misunderstandings. Retrograde rotation of planet, spinning backward. It sounds obvious. If most planets spin one way and Venus spins the other, that's retrograde. But the issue is far more subtle, because in astronomy, it's not just which way it spins, but also how much the axis is tilted. And Venus's axis is where the story starts getting weird to the point of beauty. Venus's rotational axis is tilted 177.36 degrees from the orbital plane, meaning it's almost flipped 180 degrees, just a few degrees short of being completely upside down. Imagine holding a globe and flipping its head downward, then spinning it in the same direction as Earth spins. From outside, you'd see it, spinning backward. That's the essence of the confusion. So is Venus really spinning backward, or is it just axis flipped and spinning prograde in its own way? Both interpretations are correct, and both speak to how unlike anyone this planet is. In the first interpretation, retrograde rotation means what we observe. Venus rotates clockwise if viewed from the solar system's north pole, while most planets rotate counterclockwise. But in the second interpretation, Venus has an almost inverted axis, meaning its north pole is below the orbital plane instead of above. With that configuration, if we shift perspective and view the spin direction as designated by Venus's actual pole, then the planet is still rotating prograde, like Earth and Mars. It's just standing on its head. For easy visualization, remember Uranus. That planet has a 97.77 degrees tilt, making it almost roll around the sun like a knocked over soda can. When Uranus spins, you can't just say it spins the right way or backward. What you see depends entirely on which way its axis is lying. Venus is more extreme. Instead of tilting over 90 degrees like Uranus, it's tilted nearly 180 degrees. If Uranus is like a kid lying sideways and spinning on the playground, then Venus is the one that's flipped upside down and deliberately holding that pose. Let me tell you an everyday image for easy feeling. You spin a top beautifully balanced on a table. Then you flick it lightly to make it wobble. If the flick is strong enough, the top's axis can tilt deeply to one side. In rare cases, you can make it almost upside down and continue spinning, but in a completely different direction from the original. From outside, you believe you just reversed the top's spin direction, when really you only changed its axis. Venus may have undergone a similar process, but scaled up to planetary size. where a collision of billions of joules, or a torque lasting hundreds of millions of years, could flip the axis of an entire world. And when the axis flips, every definition of spinning the right way and spinning backward becomes relative. Whichever interpretation you choose, Venus spins backward or Venus is flipped upside down and spinning prograde in its own way. One thing remains: no planet in the solar system behaves like Venus. It's the exception to the exception, a gentle taunt from nature to anyone who believes planets must follow simple, neat rules. Venus proves that sometimes just tilting the axis a bit okay. Tilting 177.36 degrees can flip your whole world view. If Venus doesn't follow the solar system's usual rules, who, or rather, what physical process pushed it onto this anti-traditional path? This is where we open the case file, and I want you to imagine in a dimly lit Sherlock Holmes-style room. On the table are 3 thick folders, each bearing the name of a potential suspect. Suspect 1, giant impact, the one believed to have struck hard enough to change a planet's fate. You know the story of Theia, the Mars-sized body that collided with Earth about 4.5 billion years ago and helped create the Moon. That's not mythology. It's a model backed by geochemical evidence from Apollo. If one collision could turn Earth into the Earth-Moon binary system, then a similar one could absolutely tilt the axis, or even reverse Venus's spin. But did Venus really endure such a heaven-shaking blow? We'll have to examine this file closely. Suspect 2. Atmospheric tides. Unlike Earth's ocean tides, Venus's atmospheric tides are strong enough to affect rotational motion. Remember that Venus's atmosphere is 93 times thicker than Earth's, with surface temperatures up to 460 degrees Celsius and superfast winds at high altitudes. A system like that isn't just an air layer. It's a gigantic machine transmitting torque to the planet's surface, which could, over time, slow and even reverse the spin. This isn't a simple suspect. It's the mysterious, elegant type, not using violence but time and subtlety. And then, suspect 3, orbital resonance, the orbital resonance phenomenon between Venus and Earth. Every 584 days, Venus and Earth are in relatively similar positions. And even stranger, in that time, Venus completes almost exactly 5 solar rotations, which makes some scientists wonder, is there some resonance lock quietly affecting Venus's rotational motion? This is the type of suspect that makes you squint. No clear action, but the behavior pattern is too coincidental to ignore. 3 suspects. 3 completely different, thrilling stories. A violent collision, a relentlessly operating atmospheric machine, and a silent but influential relationship with Earth. If this were a Sherlock Holmes detective story, you and I are standing before a pinboard full of notes, red strings connecting from Venus to 3 big question marks. And our task now is to follow each clue, peel back each layer of mystery to see what really reversed this planet's motion. Because in science, like in detective work, you never trust the obvious culprit. You must follow the evidence. And let's see, among these 3 suspects, who is really behind Venus's legendary U-turn. So we open the first file. Giant impact, the suspect of the one strike is enough to change planetary history type. When scientists simulate giant collisions during the solar system's formation phase, they often use a technique called SPH, smoothed particle hydrodynamics, a model that allows tracking how each particle of matter collides, melts, vaporizes, and reaccumulates after a horrifyingly energetic impact. And when I say horrifying, I'm not kidding. A planetary scale collision has energy on the order of 10 Hz squared. To 10 Hz, that's more than all the energy humanity has ever produced throughout history, multiplied by trillions upon trillions of times. With that kind of energy, flipping a planet's rotation axis, slowing its spin, or even reversing its rotation direction isn't too far-fetched. The entire solar system has seen it before. The most famous case is the hypothesized collision between Earth and a Mars-sized body named Theia about 4.5 billion years ago. The result of that impact was the formation of the Moon, not just a beautiful hypothesis, but one backed by extremely strong evidence. Apollo rock samples show that the 017/08 isotope ratios between Earth and Moon are almost identical, suggesting the Moon was once part of Earth. When two bodies get blended together by a cosmic smash, you expect to see similar chemical fingerprints. And this opens a big door for the giant impact suspect in Venus's file. Because if one collision could turn Earth into the Earth-Moon binary system, then why couldn't a similar one, but with a different configuration, flip Venus's axis upside down? In recent SPH simulations, scientists have thrown in every possible scenario. The impactor coming from ahead of the orbit, behind the orbit, head-on, off-center, shallow angle, deep angle, and the results are worth sitting up straight for. Many types of collisions can lead to a planet with slow rotation and potentially retrograde spin like Venus. An oblique angle collision, not strong enough to shatter the planet, but enough to make it wobble, could push Venus's axis past 90 degrees, then 120 degrees, then 150 degrees, and if the hit is precise enough, it could flip the axis to the other side, creating a planet rotating in the opposite direction from its original. In other words, you don't need to destroy Venus to make it spin backward. You just need to push its axis past the breaking point. But the most striking thing is, Venus has no moon. This makes many people doubt whether the giant impact really happened. But be careful. Earth only kept its moon because the post-impact debris stayed in a stable region at the right distance. If the debris was too close to the planet, it fell back. Too far, it could be ejected from orbit. Venus is closer to the Sun and experiences stronger tidal forces. So if it once had a moon after an impact, that moon could have been pulled down, torn apart by tidal forces, or fallen back to the planet in just a few million years, a blink in astronomical time. And in SPH simulations, published over the past decade, there are scenarios showing Venus could have been heavily impacted and yet not retain a long-lived moon, meaning the absence of a satellite isn't enough to rule out this suspect. It's like someone slamming a top hard enough to make it spin backward, except in this case, the top weighs 4.87 times 10 squared hecogram. Can you even imagine how massive that hit had to be? A light flick is enough to make a toy top wobble on its axis, but a collision strong enough to flip Venus's axis to 177 degrees? That's not an accident. That's a planet-destroying level event. And if it really happened, it would have left a completely different Venus from the original, slower, more tilted, and spinning opposite to the rest of the solar system family, as if trying to forget the fateful blow from the dawn of time. But just as giant impact starts looking like a formidable suspect, we hit a huge hole that forces us to pause and ask, if Venus once suffered a collision strong enough to flip its axis or reverse its rotation, then where is its moon? Because according to the usual logic of planetary collisions, an impact with 10 squared at 10 squared joules of energy doesn't just change rotational motion, it also produces a colossal amount of debris, molten and vaporized material that then reaccumulates around the planet. That's exactly how we explain Earth's moon formation. Debris from the Earth-Theia collision coalesced into the Earth-Moon system we see today. So if Venus went through a similar collision, why doesn't it have a moon? This is the point that makes many scientists hesitate about the giant impact suspect, a collision strong enough to flip a planet's axis, yet leaving no satellite behind sounds like a murder with no body. But when you look deeper into Venus's orbit and environment, things get more nuanced. First, Venus is too close to the Sun. This pushes the synchronous orbit the orbit where a satellite would be tidally locked to the planet's rotation. Much farther out than in Earth's case, a satellite needs to be beyond the synchronous orbit to survive long term. Otherwise, tidal forces will cause it to lose orbital angular momentum, spiral inward, and eventually fall back to the planet. For Earth, synchronous orbit is around 42,000 kilometers, but for Venus, with its extremely slow rotation, this orbit is calculated to be unrealistically far for post-impact debris to occupy, meaning any material orbiting Venus would be at risk of being pulled down to the surface by tidal forces in a relatively short time, just a few million years. And a few million years in the 4.5 billion year lifetime of the solar system is nothing. From nature's perspective, it's just a blink. This leads to an interesting hypothesis proposed in 1983 by West and Cowler. Venus may once have had a moon, but that moon was destroyed or fell back to the planet due to a process called tidal resonance a form of tidal resonance that made the satellite's orbit unstable. As Venus gradually slowed and moved toward its current retrograde state, the constantly changing tidal field could have thrown a young moon's orbit into chaos, pulling it into the planet where it vaporized in the thick atmosphere. In other words, if Venus ever had a moon, it could have been completely erased, leaving no trace, no fossils, no debris, nothing. Because, you see, giant impact both looks like the perfect culprit and like a suspiciously clean suspect. A planet-scale collision should leave evidence. But Venus, if it ever had a moon, let nature wipe it all away, as if someone cleaned the crime scene before we could figure out what happened. Or, as I might joke, a case where all the evidence has been tidied up by the perpetrator. That means giant impact isn't ruled out. On the contrary, it remains a powerful suspect, just one that knows how to cover its tracks. Still, in science, being plausible isn't enough. We need to look at the other suspects' mechanisms that could work quietly over billions of years without leaving obvious traces. Those that don't kick the door down with a bang, but whisper into the planet's dynamical structure until it spins backward from its entire family. But the giant impact story doesn't end there, because even if we temporarily accept the possibility that the killer cleaned up the scene, there's still another issue that makes this suspect too slippery to pin down. In 2025, a series of planetary collision simulations published in the journal Icarus revealed something that both excited and puzzled the scientific community. There are too many types of collisions that can produce a Venus exactly like the one we see today. That sounds great because it shows giant impact can reproduce Venus's rotation conditions, but from a scientific perspective, it's a red flag. To make it clearer, imagine you're tuning an SPH model with dozens of parameters: impact angle, impact velocity, impact of mass, approach direction ahead or behind the orbit, relative position of the sun, ratio of vaporized to melted material. And the astonishing thing is, in those simulations, many combinations produce nearly identical results: a slowly rotating planet, large axial tilt, even retrograde rotation. Some simulations show that just a glancing blow at around 10 kilometers slashes is enough to push Venus's axis past the 90-degree threshold, turning it into a backward-spinning planet. Others show a collision with an object only 1/20 Venus's mass could slow the initial rotation to nearly a standstill, setting the stage for atmospheric tides or other mechanisms to continue slowing and then reversing it later. Meaning, mathematically giant impact can explain too many things. And this is when scientific conscience speaks up. In science, a good hypothesis isn't one that can explain every outcome. On the contrary, it must have limits, must make predictions that can be wrong in some cases. If you have a model where tweaking a few parameters lets it simulate any rotation state for Venus prograde, retrograde, fast, slow, slight tilt, extreme tilt, then you don't really have a model. You have a story-generating machine. And such a model, from a methodological standpoint, cannot be considered an explanation. If your model explains everything, then it really explains nothing. A model that can produce any result just by turning adjustment knobs is no different from a skilled improvising fortune teller. You can't use it to predict, only to retroactively justify what already happened. And science doesn't work that way. So even though giant impact is a strong suspect, the 2025 simulations show it has a very big problem. It's too flexible. It has motive, means, and dozens of ways to commit the crime, to the point that it's almost impossible to prove it actually did. The case of Venus, therefore, cannot be closed with a firm conclusion that giant impact definitely happened. In fact, the opposite. Its excessive flexibility makes this hypothesis an even more suspicious suspect. And that's when we must open the next file, a more sophisticated suspect. One that doesn't use violence but can patiently alter a planet's fate over billions of years. Atmospheric tides. A perpetrator that doesn't slam the table loudly, but has the ability to change the motion of an entire world with tiny, continuous, relentless nudges. If giant impact is the noisy suspect who likes to act in a one-hit-and-done style, then the second suspect, atmospheric tides, or atmospheric tides, is a completely different kind of criminal. Patient, silent, persistent, and dangerous in a chillingly smooth way. This is the kind of mechanism that doesn't change a planet's rotation direction overnight, or in a million years, but over hundreds of millions or billions of years. It can deliver tiny, tiny pushes, but enough to alter the destiny of an entire world. And if there's any place in the solar system where this mechanism could become the dominant force, it's Venus, the planet with an atmosphere so thick it's almost paradoxical. Look at the numbers. Venus's atmosphere is 93 times thicker than Earth's, meaning if you stood on Venus, and I strongly advise against trying, the air pressure crushing you would be equivalent to being submerged 1 kilometers underwater in the ocean. The composition of that atmosphere makes the story even more ominous. 96.5% so and so and so. Pray 5% 9 cares so and so. Plus small amounts of suspended H so and so. Vapor and sulfuric acid cloud stuff that, if it got on your clothes, would eat through them before you realized what was happening. Venus's air isn't just thick, it's hot to an absurd degree. Surface temperature around 725 K or 462 degrees Celsius hotter than the surface of a smelting furnace. But it's precisely this thickness and heat that makes atmospheric tides a powerful suspect in the case of why does Venus spin backward. Imagine what happens every day on Earth when the sun shines, the ground heats up, air expands and creates a thermal lag. But on Venus, this thermal lag is amplified to the point of becoming a real torque. When part of the atmosphere heats up, it doesn't immediately rotate in sync with the sun's position. Instead, it bulges, creating an atmospheric bulge slightly ahead of where the sun is shining. And when you have a massive gas bulge pulled by the sun's gravity but offset from equilibrium, that creates a torque, and this torque acts directly on Venus's rotation. But the most important thing is that torque pulls in the direction opposite to the current rotation, meaning atmospheric tides don't just slow Venus. Under certain conditions, they can drag the planet into a retrograde rotation, state opposite direction. This was first proposed back in 1969 by researchers Gold and Soter. They argued that if a planet has an extremely thick atmosphere and spins slowly enough, atmospheric tides stop being a minor force like on Earth and become a serious player, capable of altering rotational motion over long timescales. The problem back then was that simulation technology wasn't powerful enough to verify it. But in the early 21st century, Korea and Laskar 2001-2003 delivered a major breakthrough. They simulated Venus using more complex dynamical models that included atmosphere-surface-orbit interactions. The results made the entire astronomy community need extra coffee to stay awake. Venus has 4 stable rotation states, 2 of which are retrograde around 243 days, exactly matching the observed value. Not only that, they found that under Venus's current conditions, the retrograde state isn't just possible, it's a stable equilibrium, like a marble settling at the bottom of one of 4 energy wells. That means retrograde rotation could be Venus's natural state in many scenarios. No collision needed, no accident, just time in a monstrous atmosphere. It's like you're pulling a boat one way, but a strong wind blows from the other. You pull, the wind pushes. You change direction, the wind shifts style. Eventually, the boat doesn't follow anyone, it finds its own direction, where it's no longer tugged. Venus's atmospheric tides are that wind, not violently strong, but persistent, continuous, and completely indifferent to which way you want the boat or planet to go. But of course, the case is never that simple. There's one big problem the atmospheric tides hypothesis must face. It only works well if Venus originally spun slowly enough. If ancient Venus spun fast like Earth, around 10 hours, atmospheric tides wouldn't have a chance to grab the rotational momentum and slow it significantly. A fast-spinning planet is like a tightly wound top. You can blow on it, nudge it lightly, or even flick it, but it keeps spinning in its original direction. Only when the rotation speed drops considerably do atmospheric tides gain the leverage to become the dominant force. Therefore, atmospheric tides, though powerful and plausible, cannot explain the whole story on their own. It needs a path clearer, a mechanism to slow Venus's initial rotation down to a level slow enough for atmospheric tide torque to take over. This reveals an interesting truth. If Venus really slowed and reversed because of its atmosphere, then the two suspects, giant impact and atmospheric tides, may have been accomplices in the crime. Perhaps a primordial collision shook Venus, slowed it, and then the thick atmosphere continued to twist the planet like tuning a radio with static interference. But to know if that makes sense, we need to keep expanding the investigation, because there's still another suspect, quieter, stranger, and perhaps the familiar acquaintance Venus meets regularly every 584 days, Earth. And that relationship leads straight to the third hypothesis, orbital resonance. This is where the atmospheric tides hypothesis becomes most interesting in a mathematical way when we look at the work of Correa and Lasker in the early 2000s. After a series of simulations and dynamical analyses of Venus's rotation, they discovered that atmospheric tides are not just a minor force slowing the planet, but actually create stable equilibrium points in the state space of its rotational motion. Not 1 point, not 2, 4 points. Meaning, if you imagine Venus's rotation as a marble on a curved terrain, there are 4 valleys where this marble can roll into and stay put. 2 of them are prograde states, with rotation periods around 73 to 77 days. And the other 2 are retrograde states, including one with a period of about 243 days, matching astonishingly well with the value measured by the Magellan spacecraft during 1992-1994, 243.243 .fixed 2 array. That's not just mathematically beautiful. It's like a sign from nature, written on the blackboard. Venus is sitting right in one of these 4 equilibrium points. And more importantly, the vast majority of simulated conditions cause Venus to fall into the retrograde attractor, the sucking valley for backward rotation. When you throw in different conditions, initial spin fast or slow, large or small axial tilt, thick or thin atmosphere, many configurations cause Venus to slowly drift toward the stable retrograde state. The stability here doesn't mean absolutely unchanging, but that if the planet deviates a bit from the 243-day value, atmospheric tides will create torque to pull it back close to the position. This is like a pendulum being drawn to its center, or a ball rolling down a valley. When it goes up a little, gravity pulls it back to the bottom. Imagine 4 valleys, 4 lowest points on a bizarre terrain. Venus could roll into any of them, but because its atmosphere is thick and hot to the point of insanity, it slides straight into the deepest valley, and that's the one that makes it spin backward. The key here isn't the existence of 4 equilibrium states, but the inevitability that Lasker and Correa's model suggests. With Venus's current structure, atmospheric thickness, high radiation orbit, slow rotation, retrograde isn't just a possible outcome, but the most likely one. If you run simulations with thousands of different initial configurations, most results converge on the 243-day retrograde equilibrium. It's like spinning a top in all sorts of ways and placing it on a slanted surface. No matter the initial spin, it still rolls to the lowest corner. The only problem? For the retrograde attractor to catch the planet, Venus has to be spinning slowly enough from the start, meaning another mechanism. Perhaps a collision. Perhaps internal interactions when young must bring Venus into the region where atmospheric tides have significant influence. But once that happens, the rest is almost automatic. Torque from the atmosphere will drag the planet gradually to the equilibrium state we observe today. These results are important because they not only explain Venus spins backward, but also explain why it spins at this speed, not much faster or slower. When you find a model that can explain both the direction and the speed of rotation, you know you're getting closer to the essence of the problem. But like every scientific case, this isn't a conviction. This is just evidence, a strong sign that Venus isn't acting randomly, but behaving like a system drawn to an equilibrium point determined by deep physical laws. And if atmospheric tides can draw 4 equilibrium valleys like that, then the next question becomes clear. What pushed Venus into the retrograde valley specifically, rather than one of the 2 prograde states? But just as we understand that atmospheric tides can pull Venus into a stable retrograde state, an important question immediately arises. The question every dynamical model must face: how can atmospheric tides overcome a fast-spinning planet? Because if Venus, in its early days, spun fast like Earth, when newly formed with a rotation period around 10 hours, then atmospheric tides, no matter how strong, are like trying to turn a ceiling fan running at maximum speed with just a breath. The air, even thick to an absurd degree like on Venus, can't create enough torque to slow such a fast spin in a reasonable time. A young fast-spinning planet is like a top wound to the max. You can blow, flick, or kick lightly, but it keeps spinning on its inertia. This means for atmospheric tides to take control, Venus must have slowed considerably before that. And this is where the story becomes interesting and more complex than ever. What slowed Venus? What braked it enough for atmospheric tides to take over and pull the planet into the retrograde attractor? There are a few suspects in this circle. The first suspect, not too surprising, is a collision. Not the massive giant impact like we discussed earlier, but a moderate collision. A hit not enough to tear the planet apart, but enough to reduce the initial angular momentum. In many SPH simulations, just an object a few percent of Venus's mass, much smaller than the Theia-Earth hypothesis, crashing in at an oblique angle, can slow Venus significantly, from a rotation period of a few dozen hours down to a few hundred hours. And once you've pulled the spin speed into the easily influenced region, atmospheric tides can do the rest. But collisions are only part of the story. Because if we always rely on collisions to explain everything in the planetary system, we'll fall into a model where anything weird is attributed to something hit it. That's not always true. The second suspect is a more subtle mechanism. Heat distribution and internal tidal damping frictional effects inside, between the mantle and core, that can dissipate angular momentum over hundreds of millions of years. When a planet has high internal temperature, its interior material doesn't spin as a rigid block, but can have differential rotation layers spinning at different speeds. The friction between these layers, combined with deformation from the sun's gravitational field, can cause internal tides, making the planet gradually lose rotational energy. This mechanism is very slow but relentless, perfect for what atmospheric tides need. A planet gradually slowing, drifting from an uncontrollable state to an easily impacted state. And then there's the third hypothesis, which many scientists think is the most likely, called the hybrid scenario. That is, collision plus atmospheric tides on two competing suspects, but two links in the same process. In this scenario, a medium-sized collision in the early days shakes Venus, slows it, perhaps tilts the axis a bit. After that, the planet's thick atmosphere, gradually heated by extreme greenhouse effect, starts creating stronger atmospheric tides, more abundant torque. And when the planet is spinning slowly enough, torque from atmospheric tides becomes the main driver, continuing to pull the planet toward the retrograde equilibrium. Imagine Venus is a large top that someone flicks hard first to make it lose momentum. Then a strong, continuous wind blows in one direction for years. The flick is the collision. The wind is atmospheric tides. The combination of those two factors could make a top completely change its spin direction, and in Venus's case, that could be why the planet now spins backward in a suspicious way. Atmospheric tides can turn a planet, but only if that planet stops a bit to listen. And it's this initial braking mechanism, whether collision, tidal damping, or both, that created the conditions for atmospheric tides to become a powerful suspect in the case. But the story isn't over yet, because there's another suspect, one that doesn't use strong hits, doesn't use heat, but uses rhythm, a strange relationship between Venus and Earth. A mysterious regular resonance may have participated in shaping Venus's rotational motion. And if that's true, then the third suspect isn't just a physical mechanism, but a subtle connection between two sister planets in the solar system. A mysterious resonance between Venus and Earth itself, which some scientists have jokingly called the eternal date between the two planets. We call it orbital resonance. To understand this suspect, let's start with an interesting number. 584 days. That's the time between two instances when Earth and Venus align in the same direction, also known as the Earth-Venus synodic period. Simply put, every 584 days, we and Venus meet in a geometric sense. But the strangeness isn't there. The strangeness is in Venus completing nearly exactly 5 rotations in that time. Not exactly 5, but 5.144 rotations, an oddly precise number that makes astronomers furrow their brows. To let you feel the subtlety of this phenomenon, if Venus spun a bit faster or slower, the number of rotations wouldn't stick to 5 down to 3 decimal places like that, meaning something in the dynamical system is keeping the rhythm between Venus and Earth. And when you see a rhythm repeating with unusual precision like that, scientific instinct tells you there might be a type of resonance, a subtle dynamical lock between two bodies under mutual gravitational influence. This idea isn't new. Back in the 1960s, Gold and Soda suspected that Venus's rotation rate isn't completely free, but might be affected by a very weak tidal resonance from Earth. This doesn't mean Earth pulls Venus, like the moon pulls our ocean tides. The distance between the two planets is so great that the effect is weak almost to the point of unmeasurable. But sometimes, in physics, what's important isn't the magnitude of the force, but the repetition. A very small force applied in rhythm with the system's period can accumulate effects over time, like pushing a swing very lightly, but at the right moment, it swings higher each time. And this is what makes the resonance hypothesis an interesting suspect. In many models, Venus seems to keep time with Earth in an unusual way, as if someone is following a metronome. It sounds like Venus is trying to keep the date rhythm with us, every 584 days showing the same face toward Earth, as if it doesn't want us to forget it. Of course, that's just for fun. In reality, the bigger question is the resonance strong enough to affect Venus's rotation? This is where the scientific community splits into two camps. One camp says, impossible. The gravitational force between Earth and Venus is too small to create significant torque. But the other camp, including Gold and Soda and some recent simulators, argues that the extremely precise repetition of the 5.1444 rotation cycle can't be just coincidence. In resonance models, just a light lock between orbital and rotational motion can create a small but sustained force, impacting the rotation rate over long times. There's a variant of this hypothesis that suggests the resonance doesn't affect the whole planet, but affects Venus's core if its core isn't completely synced with the mantle. In that case, Earth doesn't need to pull all of Venus. Just a small deviation in the core's moment of inertia could amplify the resonance impact. And this leads us into part 13, where we'll examine the core-mantle decoupling hypothesis. But before stepping there, let's emphasize one important thing. The resonance hypothesis is very elegant. It doesn't need a collision, doesn't need a thick atmosphere, doesn't need violent events. It just needs time and rhythm. But like every other elegant suspect in detective stories, that elegance makes it hard to pin down, the force too small to measure, the effect too subtle to prove immediately. Still, the strange precision of 5.144 rotations every 584 days stands there like a big question mark in the case file. Do Venus and Earth have a deeper connection than we think? Or is this just a suspiciously beautiful coincidence? When we talk about resonance between two planets, we often think of a grand dance orbits around the sun, period times, massive gravitational forces interacting. But there's a much more subtle variant of this idea. And it leads us deep to the point where we're no longer discussing Venus's acid clouds or molten surface. Instead, we step into the very heart of the planet, the metal core, where a hypothesis both subtle and astonishing was proposed in 2010 by researcher C.C. Cottrell. His idea is simple but strangely compelling. What if Venus's core doesn't spin in sync with the outer mantle? In other words, what if this planet has a heart spinning to its own rhythm, a rhythm sensitive enough to be affected by forces that the outer shell barely feels? This is an important twist, because if the core and mantle aren't synchronized, even the very small gravitational force from Earth, which many scientists say is too weak to affect the whole planet, could still leave an imprint on the core. In planetary physics, this is called core-mantle decoupling. The core and mantle aren't a single rigid block, but can spin slightly offset, with internal friction and tidal interactions acting as the door opener for small forces to amplify. Imagine holding a hard-boiled egg. You spin the egg hard, and you see the white spinning smoothly. But the yolk inside, it spins differently, slower or faster a bit. And if you suddenly change direction, the yolk's inertia makes the whole egg have quirky motions. Notably, Earth has very distinct core-mantle separation. Our outer core is liquid metal, inner core solid metal, and neither always spins in sync with the mantle. That phase difference is part of why Earth has a strong magnetic field. In contrast, Venus is still a big mystery. Is its core liquid or solid? Does it have separation as clear as Earth, or is it stuck tight to the mantle like a giant molten rock? The irony is that the overly thick atmosphere, overly high temperature, and immense pressure make sending seismic equipment to the surface nearly impossible, leading to us not knowing how Venus is beating inside. And that's where Cottrell's hypothesis becomes appealing. He argues that if Venus's core isn't locked tight to the mantle, it could move slightly differently. A small offset alone is enough to create a difference in moment of inertia. When Earth and Venus enter the 584-day resonance rhythm, the small tidal force from Earth doesn't affect the entire planet, but affects the core lightly touching the spinning yolk in the egg, creating a very small but repeating shift in a certain cycle. Over millions of years, these small touches can accumulate, creating torque on the mantle if the two layers aren't fully synchronized. And this is where the hypothesis becomes beautifully suspicious. Remember the strange number we've seen. In each 584-day Earth-Venus cycle, the planet spins 5.144 rotations. If Venus's core has a rotation speed slightly different from the mantle, that 5.144 rhythm could be the resonance frequency. Just like pushing a swing gently, but at the right moment makes it swing higher over time. To visualize, if Venus's mantle is like the egg white spinning outside, the metal core, the yolk spinning inside, and Earth, the one tapping lightly on the egg in rhythm, then those taps, though very small, can accumulate like push-push-or in a fixed cycle. But an important question arises. Is Venus's core really separated like that? We don't have an answer yet. No seismometers on Venus, no moon to measure tidal deformation, no significant magnetic field data, since Venus has almost no protective magnetic field like Earth. Some models suggest Venus's core may still be hot enough to maintain a liquid state. Others say the core has cooled and become solid or semi-solid, making the mantle and core nearly locked tight, limiting slippage between layers. But whichever way the answer leans, the core resonance idea is still a valid and appealing theoretical framework because it explains two things at once. Why Venus maintains a 5.144 rotation ratio per Earth meeting. Why Venus's rotation could change slowly over time without needing a large force. And this is where you see a very characteristic trait of planetary science. The deeper you dig, the more refined the hypotheses become. Not the big collision flips everything backward kind, but the tiny repeating resonance rhythm over hundreds of millions of years affects the core, then transmits to the mantle kind. It's like comparing a punch to a melody. The punch creates big change immediately. The melody creates small but lasting change, if you're patient enough to hear the whole song. Weird, really. A planet flipped, not because something hit it hard, but because it kept getting lightly tapped in rhythm for millions of years. Like the yolk and white suddenly hearing the same tune. But this hypothesis still can't conclude. It lacks core data. It lacks seismology measurements. It lacks magnetic field for reference. However, it raises an important question that science will have to answer. If Venus's core really spins differently from the mantle, then how much of what we observe changing rotation speed? 5 no's, 1 resonance. Retrograde rotation is due to external forces, and how much is due to the planet's heart spinning to its own rhythm? This planet seems not to maintain a fixed rotation speed, as if it's changing its spin rhythm over time. This isn't vague speculation, but is proven by hard data from the 2 largest observation missions humans have ever conducted on Venus. The Magellan spacecraft, operating from 1991 to 1994, used radar mapping to measure the planet's rotation speed with extreme precision and obtained the figure 243.01.85 days for 1 full rotation. This became the foundational value the scientific community used for decades, because Magellan scanned nearly the entire surface of Venus with cloud-penetrating radar, something no optical telescope could do. But then came the 2006-2012 period, when ESA's Venus Express orbited the planet and made independent measurements, and something strange appeared. Venus's rotation period seemed about 6.5 minutes slower than Magellan's result. 6.5 minutes. It sounds tiny in human life, but for a planet with a mass of nearly 4.87 times 10 squared for deal zinth, now's a very significant change. A planet whose rotation speed isn't stable is a planet that big, yet keeping time like a water-damaged wristwatch. It doesn't run so wrong that you throw it away, but enough to make you unable to trust the time it shows. So what's going on here? Why is Venus, which is already strange in its rotation direction, even stranger in its rotation speed? There are three main suspects for this 6.5-minute change, and each opens an interesting door into planetary mechanics. The first suspect, exchange of angular momentum with the atmospheric angular momentum exchange. Remember that Venus's atmosphere is nothing like Earth's. It's thick, hot, and especially features a phenomenon called superrotation, where the upper atmospheric layers circle the planet in just 4 days, 60 times faster than the surface rotation speed. When such a high-velocity gas layer continuously rubs, slips, pushes, and pulls against the planet's surface, it can transfer a small but gradually accumulating amount of momentum. If the atmosphere speeds up or slows down in certain layers due to changes in solar radiation, that momentum can leak into Venus's rotational motion, making it slow down or speed up gently, like a wheel brushed by wind from the side. The second suspect, core mantle friction. If Cottrell's hypothesis from earlier is correct, that Venus's core might spin slightly out of sync with the mantle, then that phase difference could cause internal friction, dissipating rotational energy. This also happens on Earth, though much more mildly. Our inner and outer cores spin at slightly different rates, and their interaction contributes to small variations in Earth's rotation speed. But on Venus, if the core is asynchronous and the mantle has high viscosity, the friction between the two layers could be large enough to cause a change of a few minutes in the rotation period over many years. The third suspect, seasonal thermal variations. It sounds odd because Venus has almost no distinct seasons like Earth, but the heat distribution on the surface and in the atmosphere still varies according to the sun's illumination angle in the planet's slightly elliptical orbit. Even a small change in absorbed solar energy can alter the flow structure in the upper layers. That in turn affects the angular momentum the atmosphere transfers to the surface. This is a non-intuitive mechanism, but in recent aerodynamical models, it's a serious candidate. What makes this story even more interesting is the change in Venus's rotation speed over time is living proof that our dynamical models are not yet complete. A planet that should be a gigantic, stable spinning machine, yet Venus spins as if it's changing its mind every few decades. Not much, not chaotic, just enough to remind you that the internal controlling mechanisms are still not fully understood. And this is precisely why Venus is a beautifully absolute mystery to every physicist. It continuously breaks every expectation, every model built to explain it. Retrograde rotation isn't enough. Orbital resonance isn't enough. Atmospheric tides aren't enough. And now it even changes its rotation speed over time, as if sending the message, you guys are still far from understanding me. But in science, this small change isn't frustrating. It's a sign that there's still much to discover. If you think the small fluctuations in Venus's rotation speed are the strangest thing this planet can do, then brace yourself, because we're about to step into a phenomenon that would make any atmospheric physicist tip their hat. Superrotation, the super-fast winds in Venus's atmosphere. This isn't the kind of strong wind you see in superstorms on Earth. No, this is a completely different dance. At the top of Venus's cloud layer, around 60 to 70 kilometers altitude, winds blow at 360 kilometers /h, and the craziest part is, the entire upper atmosphere completes one full circle around the planet in about 4 Earth days. For comparison, the surface of Venus takes 243 days to complete one rotation. That means the atmosphere spins 60 times faster than the surface. You can imagine how out of this world this phenomenon is. Venus spins so slowly, it's like taking an extended nap, while its atmosphere races around like a jet turbine in test mode. No other planet in the solar system does anything similar with such extremity. Even Titan, Saturn's moon, has superrotation, but nowhere near the 60,001 ratio. If I had to sum this up with an image for you to picture easily, it's like you standing completely still, motionless, while the coat you're wearing spins around you once every few seconds. The important thing is, the atmosphere doesn't just spin fast, it spins uniformly, in a stable dynamical pattern, making Venus's entire cloud layer seem glued to a gigantic conveyor belt wrapped around the planet. This creates one of the biggest puzzles in planetary meteorology. How can such a thick, hot atmosphere, subject to huge frictional forces, maintain such extreme velocity over long periods? Not just a few years, but millions of years. And scientists have been chasing this question for over half a century. Part of the answer lies in Kelvin waves, planetary scale atmospheric waves, sustained by the Coriolis force and heat distribution in the atmosphere. On Earth, Kelvin waves play a key role in phenomena like the MJO, but on Venus, due to the slow rotation speed and extreme temperature differences, Kelvin waves become true marathon runners, transporting energy along the equator and helping drive the atmosphere around the planet. A second mechanism is thermal tides, the same thing we discussed when talking about retrograde rotation. But in Venus's upper atmosphere, thermal tides don't just create torque on the planet, they also generate gigantic flow patterns, driven by the phase lag between solar radiation and the atmosphere's peak temperature. Thermal tides create moving high-low pressure zones, and when these interact with Venus's already very weak Coriolis force, they help sustain large horizontal wind speeds. This is like a series of aerodynamic gears continuously pushing the atmosphere faster and more stably, like an engine that never shuts off. The most crucial factor, creating the quantitative difference between Venus's superrotation and that of other planets, is momentum transport, the transfer of angular momentum through the atmosphere. Venus has planetary scale flows that transport momentum from the equator to the poles, from lower to upper layers and back. Upwelling flows in the day side carry inertial momentum, move to the night side, then sink again, forming an extreme Hadley circulation unlike anything on Earth. In each cycle, a portion of momentum gets locked into the high cloud layer and gradually accumulates, creating terrifying wind speeds. One thing that drives scientists crazy is superrotation occurs without significant contribution from the planet's baseline rotation rate. Venus spins so slowly that the Coriolis force is dozens of times weaker than on Earth. Yet it's precisely on this planet that atmospheric superrotation appears the strongest. That means Venus's superrotation isn't borrowed from the planet's spin, but is self-generated by the atmosphere itself, by arranging incoming solar energy in a way that favors horizontal motion. And the most shocking truth, aerodynamical models show that superrotation is a self-sustaining phenomenon. Meaning if you stop the winds in a simulation and let the atmosphere start spinning again from scratch, the system tends to return to the superrotation state if that's its natural equilibrium point. This makes superrotation a crucial piece in the Venus case file, because when the atmosphere spins 60 times faster than the surface, angular momentum from the atmosphere can leak down to the surface, affecting the planet's overall rotation rate. The very thing we saw in part 14, an atmosphere spinning 60 times faster than the surface, isn't just weird, it's a powerful mechanism that can transmit torque from atmosphere to planet, changing rotation speed over time. If atmospheric tides are the silent pusher shoving the planet into retrograde, then superrotation is the accomplice, the one that keeps fine-tuning Venus's spin rhythm over long periods. And finally, when we look at the big picture, we realize Venus's backward spin isn't just a story about axis and momentum. It's a story about atmosphere, about heat, about planetary scale waves, and about a world operating under laws that human intuition nurtured on Earth can't possibly predict. If planets are dancers at the sun's party, then Venus doesn't just dance offbeat, it spins in its own style, at its own speed, with an acid cloud dress swirling 60 times faster than its own footsteps. When it comes to Venus, the irony is that we understand a great deal about its atmosphere, its orbit, the kinematics of its cloud layers, but we understand extremely little about its surface. Not because we don't want to know, but but because Venus is where human technology goes to die. If you want to know the real limits of robotic engineering, you don't need to build pressure test chambers, create vacuum rooms, or plasma furnaces. Just send a robot to Venus. If you want to test durability, send a robot to Venus. It will show you technology's limits faster than any lab test ever could. And that's not a metaphor. The history of human exploration of Venus, especially by the Soviet Union, is a series of tragedies where sophisticated machines, painstakingly built over years, lived on the planet's surface just long enough to send a few signals before dying in an environment harsher than imagination. Let's start with Venera 7. This was the first spacecraft in human history to successfully land on the surface of another planet besides Earth. But when I say successfully, it only means it touched down and remained operational for a very short time. Venera 7 survived 23 minutes before the temperature and pressure around it paralyzed its entire electronic system. Some of the data it sent back is still debated to this day, because the signal was so weak that engineers had to manually filter every millisecond to confirm the craft was still breathing in its final minutes. Then came Venera 9 in 1975. This was the first spacecraft to send back direct images from Venus's surface, an iconic achievement. You'd think we'd get a full 360-degree panorama, but no. Venera 9 only sent half the image, because the other half of the camera was blocked by a protective cover that failed to detach as designed. And even with just half the truth, it still made history. However, Venera 9 didn't live long either. Death came as quickly as for every other mission. Equipment overheated, metal structures began to deform, and electronics shut down. In its final minutes, it still transmitted some data on illumination levels and pressure. Then silence. And then among the toughest machines ever sent to Venus, Venera 13, 1982, stands out. This was a spacecraft designed to endure death. It had multi-layer thermal insulation, a chemical cooling system using frozen mixtures, and an outer titanium alloy shell built to withstand pressure. It landed on Venus and survived for 127 minutes, more than 2 hours, a near absurd feat in that hellish environment. In those 113 minutes, Venera 13 sent back the first color photographs from the surface, recorded the sound of Venus's wind, analyzed soil samples with spectroscopy, and measured sky brightness optically. After that, like all the other brave machines, it was slowly roasted to death. Not due to technical failure, not due to design error, simply because no material known to humans can survive long in those conditions. Look at the numbers to understand the problem. 462 degrees Celsius hot enough to melt lead. 93 atm pressure equivalent to the weight of water pressing on you 900 meters underwater. And an atmosphere full of sulfuric acid ready to corrode anything. Every lander was a desperate test of material science. Insulation held for only minutes before heat penetrated. Metal shells stayed rigid for only tens of minutes before losing strength. Electronics, even heavily shielded, couldn't withstand the extreme heat and pressure. Venus isn't just a hot planet. It's a robot-destroying factory. And this makes every effort to understand the planet's surface extremely difficult. You want to measure petrology? Robot dies. You want to measure seismology to understand the core? Robot dies faster. You want a survey lasting hours? Dream on Venus will crush your spacecraft like crushing a soda can. The astonishing thing is, even if humans built machines 100 times more advanced than Venera, they still couldn't survive this environment. For decades after Venera, no spacecraft dared to land directly again. All modern missions like Venus Express chose to orbit high above, never touching the ground. Not due to lack of technology, but due to lack of materials. To land on Venus long-term, we need extremely powerful cooling technologies, ultra-refractory alloys, electronics that operate at 500 degrees Celsius without melting, all of which are still in the research phase, not application. And this is the point that makes the Venus case even harder to solve. Every piece of data we have about the surface, geological structure, seismic vibrations, internal mass distribution, everything is seriously lacking. Venus is a locked room where every time we try to open the door, the key melts in our hand. When we look back at what human robots have gone through on Venus, those brief, fleeting moments of survival and hell, we realize the biggest problem in the entire case. We don't truly know what Venus looks like on the inside. We have models, hypotheses, faint, blurry traces of radar data from orbit, but the most important things are completely absent. First of all, we have no seismic data whatsoever from Venus. No seismometer has ever survived long enough on the surface to measure the planet's vibrations. That means we don't know whether Venus's core is liquid or solid, how big it is, whether it has layering like Earth's or is a solid block from inside out. If the core is liquid, core-mantle decoupling is feasible. If the core is solid and tightly adhered to the mantle, that hypothesis falls apart. But right now, we only have speculation, not just a core. We also have no rock samples from Venus's surface. The moon gave us hundreds of kilograms of samples. Mars is poised to have samples returned in the coming decade. But Venus? Not a single grain of dust. The Venera probes had in situ analyzers, but those were only instantaneous measurements, not samples brought back for detailed analysis with modern technology. No rock samples means we don't know Venus's mineral structure, degree of thermal alteration, geological history, or even whether the surface was ever completely resurfaced due to global volcanic activity. Some models suggest the entire Venus underwent resurfacing around 300 to 700 million years ago. But is that accurate? No one knows. Another gap is the lack of long-term rotation monitoring. We know Venus's rotation period changed by about 6.5 minutes between the Magellan era, 1991-1904, and Venus Express, 2006-2012. But is this a long-term trend, or just short-term variation? No one has measured long enough to know. We don't even know what Venus's rotation period will be in 50 or 100 years, an astonishing thing to say about a planet only a short cosmic distance from Earth. These deficiencies aren't due to a lack of scientific effort. We don't know because Venus kills every machine, not because we don't want to understand, but because we can't send anything that lives long enough to observe. But the story doesn't end in disappointment. In the coming decade, 3 major missions promise to completely change our understanding of Venus if they actually get launched. First is NASA's Playful, a mission using high-resolution radar and gravity field measurements to map Venus's surface and internal structure with unprecedented accuracy. But this project has been delayed until after 2031, causing major disappointment in the scientific community. Next is DAYS PAC+, also from NASA, planned for the 2030s. This mission will drop a probe through Venus's atmosphere, measuring chemical composition, thermodynamic structure, pressure, and possibly helping us understand the history of that thick atmosphere, whether it once resembled young Earth's or not. And finally, ESA's Envision, scheduled for launch around 2031, designed to study the relationship between Venus's surface, atmosphere, and geological activity. This mission could tell us whether Venus still has volcanic activity or is geologically dead. These 3 missions, if completed, could provide the missing pieces to decode why Venus spins retrograde, why its atmosphere is so insane, and why Earth's sister planet chose such a completely different fate. But until we have that data, the case still lacks the most important clues. We're trying to explain the behavior of a planet where we've only seen the outer layer and a tiny bit inside, like trying to guess someone's personality just by the coat they're wearing. There's still so much data missing, and it's precisely that lack that makes Venus the most enduring mystery of the solar system. When thinking about the mystery of Venus, it's easy to see it as an isolated case of bizarre world, just to satisfy scientific curiosity. But the reality is far deeper, because Venus and Earth are the twin pair of the solar system. And Venus's story isn't just about itself. It also tells us what could happen to Earth if things on our home planet go just slightly off track. Let's start with the numbers that make these 2 planets suspiciously similar. In size, Venus has a diameter about 95% of Earth's. In mass, about 81%. Both are terrestrial planets, primarily composed of silicate mantle, iron core, and a thin crust. Average density? Almost identical. If you put Venus and Earth in a closed box and could only feel them by hand, you'd have a hard time telling which is which. They were born close together, from the same disk of dust and gas, under the same conditions of the young system. Twin planets, at least on paper. But that's where the similarity ends. Because when you open that box and look at the atmosphere, temperature, pressure, and internal dynamics, you no longer see two sisters. You see two fates, so opposite it sends chills down your spine. On Earth, average temperature is about 288 K, 15 degrees Celsius. Breathable, livable, easily allowing liquid water. On Venus, 735 K, or 462 degrees, hotter than a smelting furnace. On Earth, atmospheric pressure is 1 atm, enough for humans to stand upright and breathe without being crushed. On Venus, 93 atm, like having an entire ocean pressing down on you. Earth has water rain. Venus has sulfuric acid rain. Earth has blue oceans. Venus has lava plains and scorching basalt rock. That stark contrast raises the big question. What made these twin planets take two completely different paths? And this is where rotation the planet's spin becomes a key character in the story. On Earth, a 24-hour day creates a stable thermal cycle. Day warms up, night cools down. That cycle regulates the atmosphere, producing wind, rain, storms, and most importantly, an energy circulation system capable of sustaining life. But Venus, with its 243 Earth day-long day, scorching hot and spinning retrograde, has no such regulation. Every surface region stays under sunlight far too long enough to heat up until the whole planet retains heat like a gigantic furnace block. No long enough cool night to radiate heat into space. This contributes to the runaway greenhouse effect, where heat accumulates in the thick coal-on-a-saccum atmosphere and never escapes. The difference in rotation doesn't just affect climate, it also affects the magnetic field. Earth has a fast-spinning liquid iron core that generates a powerful dynamo building a protective magnetic field against solar wind. Venus spins so slowly the dynamo barely functions. This planet only has a weak induced magnetosphere from solar wind interaction, not strong enough to shield the atmosphere or prevent erosion by high-energy wind. Weak magnetic field. Atmosphere gradually stripped by solar wind over time. But because Venus spins slowly and the greenhouse effect is so strong, core K evaporates from the surface and volcanoes to replenish, a perfect vicious cycle turning an Earth-like planet into a high-pressure hell. If Earth could turn into Venus, we'd better understand what Venus is like. Because what happened on Venus isn't some freak accident in a corner of the solar system. It's a possible outcome for a rocky planet receiving too much radiation, retaining heat too well, losing balance in its rotation, or undergoing climate change beyond natural regulation. In other words, Venus isn't just a world to gaze at through a telescope. It's a warning, a dark mirror, proof that two planets born alike can end up at opposite extremes just because a few physical parameters shifted rotation axis, spin speed, distance from the sun, volcanic activity, atmospheric composition. And when we investigate why Venus spins retrograde, why its atmosphere superrotates, why its core might spin differently from the mantle, we're doing more than solving a distant puzzle. We're learning about our own habitability. And when we stand before all the missing data, the incomplete models, the hypotheses of impacts, atmospheric tides, core and orbital resonances circling each other like unfinished loops, I can't help but recall one of the most important philosophies in science of philosophy, that science sometimes forgets in its pursuit of absolute certainty. He said, I would rather have questions that can't be answered than answers that can't be questioned. And if there's any place in the solar system that forces us to acknowledge this with full humility, it's Venus. Look back at the journey we've taken. We have a planet almost twin to Earth, yet hotter than a forge, spinning retrograde as if challenging every rule of planetary formation, with a gigantic atmosphere swelling 60 times faster than the surface, with a rotation rate changing by decades, possibly impacted or not, possibly with a decoupled core or not. And we have no direct way to measure the core, measure seismology, or even keep a robot alive more than 2 hours on the surface. That's not a failure of science, that's science. Because the essence of science isn't rushing to give answers, It's honestly admitting we don't have the answers and continuing to ask. When you believe you know everything, you lose the ability to learn anything more. And Venus, in its own way, is an uncompromising teacher. It reminds us that the universe doesn't exist to satisfy human intuition. It has no obligation to be reasonable by our expected definitions. When we think all planets must spin the same way, Venus smiles and spins backward. When we assume rotation speed must be stable, Venus changes its rhythm by 6.5 minutes. When we think a thick atmosphere would block wind, it creates super rotation at 360 kilometers/h. Every detail of Venus is a reminder you don't understand yet. And this isn't disappointing. This is what makes science alive. Because if Venus behaved exactly like Earth, we'd learn nothing from it. But precisely because it breaks the mold, precisely because it forces us to keep re-asking questions, we realize the true depth of the scientific method, not assertion, but doubt, not imposition, but observation, not cramming all data into a comfortable explanation, but accepting when the explanation hasn't appeared yet. It's a mirror reflecting the limits of our understanding. It forces us to recognize that not every question can be answered today. Not every hypothesis can be tested. Not every mystery will be solved immediately. But that doesn't diminish the mystery's value. On the contrary, it makes the journey of discovery more profound, because the honesty of science doesn't lie in saying, "I know." It lies in having the courage to say, "I don't know, but I want to know." And if Venus has one lesson to teach us, one that goes far beyond its acid atmosphere, molten surface, or strange rotation axis, it's the lesson of intellectual humility. Because if we want to understand why Earth remains a green paradise, and why Venus became a scorching hell, we must start from the point where all true science begins, acknowledging ignorance. And when looking back at the entire bizarre case surrounding Venus, it's time to gather the main suspects on the table and see who is truly the most suspicious. The first suspect, giant impact, remains an appealing choice. It's a simple, familiar explanation. Something large slammed into Venus, slowing it down, tilting its axis, or reversing its spin. We know such collisions have happened many times in solar system history. The here Earth impact that created the moon is the strongest proof. And SPH simulations show a whole range of impact configurations that could produce today's Venus: slow rotation, large axial tilt, even retrograde. The only problem with giant impact is it explains too much. When a model can produce almost any outcome just by tweaking parameters, you no longer know if it's describing the true nature of the world or just indulging the user. On top of that, Venus has no moon inertia that makes the strong impact model hard to prove, even if it doesn't fully invalidate it. The second suspect, atmospheric tides, is the opposite picture. No violence, no accident needed, just time and a crazy 93 atom thick atmosphere. And the wonderful thing is, atmospheric tides aren't just beautiful in physical language. They're elegant in a mathematical sense. They create 4 stable equilibrium points. And Venus is sitting exactly in one of them, retrograde 243 days. Not approximately, not similarly, but exactly matching Magellan's observed value. This is the kind of structured coincidence science loves, because it doesn't just explain why Venus spins backward, it also explains why it spins at this speed, not much faster or slower. Atmospheric tides has a weakness. It needs Venus to be spinning slowly from the start. But this opens a strength. It integrates well with giant impact in a hybrid scenario. A collision slows the planet, and atmospheric tides finish the job. The third suspect, orbital resonance with Earth, is beautiful in a subtle, mysterious way. The number 5.0134 rotations per Earth-Venus alignment, 584 days, is one of those oddities that makes any dynamicist stop and think, is this really just coincidence? But resonance, while intriguing, is too speculative. The gravitational force between Earth and Venus is weak, not strong enough to explain everything unless there's core mantle decoupling, plus a chain of other delicate conditions. It's not ruled out, but it can't stand alone. Resonance is like the shadowy character in a detective story, present in many scenes, possibly playing some role, but never caught red-handed at the crime scene. When we put the three suspects side by side, it's hard to point at one and say, this one, it's him. Giant impact has good motive, good means, but lacks evidence. Atmospheric tides has a beautiful model. Mathematical support, but needs the right initial conditions. Resonance has the grace of a rhythmic explanation, but lacks clear mechanical power. Believe in whichever hypothesis you want, as long as you don't believe in it too much. That saying isn't a joke. It's the heart of the scientific method. It reminds us that every explanation is temporary, every conclusion can be improved, and every model must be ready to be replaced by a better one when new data arrives. So if we have to pick the most suspicious suspect with current data, many scientists would choose atmospheric tides, with an initial collision playing the necessary braking role. But Venus still has too many mysteries for a final verdict. This case, like many of nature's most beautiful mysteries, isn't meant to point out the culprit. It's meant to remind us that the universe isn't simple, and that the process of understanding it is science's greatest joy. The very strangeness of Venus is what makes science so beautiful. If Venus were like Earth spinning in the same direction, with comfortable temperatures, a gentle atmosphere, everything reasonable, we wouldn't have learned anything from it. But Venus, with its day longer than its year, with winds swirling 60 times faster than the surface, with an orbit that makes it complete exactly 5.144 rotations every time it meets Earth, with a rotation rate that shifts unpredictably, like a water-damaged watch demands that we dig deeper, think bigger, ask better questions. Paradoxes like these are exactly what make scientists wake up in the morning with a sense of excitement, because nothing stimulates curiosity more than facing something that clearly doesn't match expectations. A planet that refuses to follow the neat rulebook we built in our minds. A story where every explanation seems right until you look closer. Science doesn't advance through easy answers. It advances through those moments when we have to exclaim, wait a second, this doesn't make any sense at all. And Venus is that centuries-long moment. It reminds us that the universe has no obligation to be reasonable by human standards. We are the ones who must learn to understand it on its own terms. In physics, sometimes a beautiful paradox is worth more than a complete solution. It's evidence that we're standing right at the edge of something important, a broader theoretical framework, a deeper understanding, a natural truth never before seen. It's no coincidence that many scientists call Venus the honesty test of planetary physics. It's the system where every assumption must be re-examined. Every model must prove its worth, and every conclusion must retain a touch of humility, an approach to the world full of curiosity, full of doubt, and full of excitement about the unknown. And when it comes to Venus, I can imagine him smiling, adjusting his glasses, and saying, if one day someone finally explains why Venus spins retrograde, I hope they still carry that same sense of wonder they had at the beginning. Because the answer isn't the end. It's just part of the journey of discovery. What makes the journey worthwhile is the feeling of encountering the mystery, touching the limits of our understanding, and knowing that no matter how far we go, nature still has many cards left unturned. And that's also why we keep looking at Venus, not just because we want to find the culprit behind its backward spin, but because we want to understand more deeply how the universe works, and through that, understand more clearly Earth's small but beautiful place in the picture. Because if Earth and Venus were born so alike yet ended up with completely different fates, then understanding the reasons isn't just a scientific exercise. It's a lesson in survival. And before closing this journey, I want to leave you with one open question, not for you to answer right away, but to carry with you like a seed of curiosity, always the most precious asset of human intellect. If it were up to you, what do you think made Venus spin backward? A collision? A symphony of the atmosphere? A mysterious resonance rhythm? Or something we'd never even imagined? Whatever the answer is, or even if the answer hasn't arrived, yet the journey to explore Venus has taught us one thing. Sometimes, the greatest beauty of science isn't in solving the mystery, but in the fact that the mystery exists. Venus reminds us that the universe is still full of surprises, and it's precisely those surprises that keep science alive, Keep it growing, and keep humans looking up at the sky with the same awe as if seeing light for the very first time. If you enjoyed this journey full of paradoxes, please subscribe to the channel so you don't miss the next stories about the universe. See you again on the next adventure, where new mysteries are always waiting to be uncovered.